Hello and welcome to the session called Model-Based Design. And I'm happy to present our first presentation. It is paper by Giuseppe Pereira, Luigi Manfrotto. Hello, and Luigi will have the presentation. Luigi, the stage is yours.
All right, thank you. So in this presentation, we're basically have been developing a library for power system dynamic simulation called an IPSL. I will not talk too much about the history of the library, but it's been, product of almost 10 years. One key component of this library is that we needed to convince power utilities, power industry people that use tools that were developed in the 1970s that Modelica can do the same thing, can give them the same results. So over that period of time, we develop certain techniques and methods to do their implementation so that it will be meet the requirements of that specific industry and cohort of people. So we decided to put together some guidelines on how to do it. So the people supporting this work was mostly Dominion Energy, who are the ones giving us all the use case for their power plants in Virginia, and they are funding the work also. And then Model took one of my PhD students and had him as an intern so that we could make the library fully compatible with Impact. And then we had a power system expert that helped us, Ricardo Software. Basically, his life is to do studies with the tools built in the 1970s, basically. So that's it's a big team effort over the many years we're trying to do. Okay, so the outline is, I'll give you a little bit of an introduction of why we tried to make this paper, some more motivation than what I already provided, the contributions that we are making in the paper, illustrate you the guidelines, and show you some use cases that were really, really tricky to implement to get the same result as the old software that is Fortran code that you cannot see. So we're trying to formalize somehow the process of implementing these power system dynamic models and verify them against de facto standard tools. Just give a sort of formal description of the steps that we have done to re-implement and verify them against this closed source commercial software that is in the North America is mandated by NERC to be used. The North American Electric Reliability Council is mandated by them to be used in the whole eastern part of the U.S. electricity system. So that's why we target that one specifically. I'll show you a couple of use cases, and then one of the key features here that we take advantage is all of the software that is used in the power industry have documentation in PDFs, and some PDFs have not only limited information but also mistakes in the model documentation. So one of the nice things of using Modelica is that it's self-documented, basically. So it allows you to capture that knowledge and keep it in a way that gives the description of the model itself with the implementation. And then I would like to show you examples of emphasizing why this is relevant for open access standardized model exchange and why this is relevant at least for this kind of work. So, modeling power systems has pretty much goes through an entire life cycle of not only power plants, but also the entire power grid itself. Is largely used in many US states as a requirement to interconnect a new plant. You actually have to do some studies. They're called interconnection studies. So it's used for planning all the way to operation. So they get a snapshot of the current operation of the system, and some tooling is available to do dynamic simulations to check it, like, okay, if we lose all these power lines, is the system going to survive? So over the last decades, they have created new tools to do this kind of studies. But really, at the end of the line, you have to be really an expert. And being a Modelica expert is one thing, but being an expert on a commercial closed-source software tool that is very has very much domain-specific idiosyncrasies is very, very difficult. So the other problem is that each tool has its own data format. There's not such thing as a model exchange there. It's only exchange of parameter files. Because the models within the tools are basically integrated into the solver, into a specific structure in the tool itself. So this leads to inconsistency. If you try to compare 3 of these tools and you want the model to give you the same answer, you actually need manual human intervention to achieve that, which leads to tremendous cost. So in the paper, actually, cited a study done by the Australian Energy Commission, I think. And in that study, the implementation of one model, for example, for a photovoltaic inverter will cost $500,000 in a specific tool. So I can send you, so the value really of this kind of work that we're trying to do is to, you do it once, you do it well, and hopefully those tools will mature enough to accept the FMI standard, and we will have a tremendous cost reduction. But the way that is done right now in the field is that a piece of equipment doesn't have a model, and they don't use model-based system engineering there, it will cost $500,000 or even more, depending on the piece of equipment, to have a model to do this kind of studies. Okay, so removing ambiguity between model implementation and tools is something that's done already through the Modelica standard, but we need to kind of show it in the other field. So we try to do this formalization of the steps of the process of doing implementation against this software called PSSE, Power System Simulation for Engineers, is what it means, and show you how so those tools, to get a simulation, you actually have to model the entire integrated system. You cannot do a simulation component-wise basis. But we can verify each of the subcomponents that we need to validate individually in Modelica. So we have an approach to do that. And I'll show you a little bit of how we do it. So, when we're building models to be validated, we basically use templates. Our template on the right-hand side is going to be the network to which a power plant is going to be connected, and the power plant is then the right-hand side. So on the left-hand side in red. On the right-hand side, then you see this template that is basically a power network that has different components that allows us to introduce and do tests. And on the right-hand side, you have a power plant representation. So Gen Rho E is a typical name model in the list of models approved by the North American Electrical Council. And that is only the electrical machine model. To it, you have connected a voltage control system, the EST1A, for example. That one has a stabilizer connected in cascade that is a PSS. And on top of it, you have a representation of the governor control system and the turbine. So those are all of these kind of models that are in the commercial closed-source tools that are accepted by the governing models in the US or in North America. And then we need to verify, and we need to verify the component-wise. So the model implementation guide is basically a series of steps in a flowchart. Basically, the first thing that you have to do, I think it's pretty hard to read. I didn't check this before, sorry about that. But basically, the first thing that you need to find out is what the hell is inside of that model, because you have zero access to the source code. So the first thing that you check is the manual of the software, and there's insufficient information. So for one of the models, for example, I had to go dig out a paper from 1974 that had all the equations, and the paper had a mistake. So we found out that the mistake in the paper was replicated in the documentation of the software, and it was science. In some blocks, basically. So being able, you have to go through this whole sort of process of study, like a human has to do this, right? So once you actually have enough information, they're usually in the form of block diagrams. Sometimes they have equations. The first thing that we do is determine if we have those blocks already available in the Modelica standard library or in our library itself. Because of how they have implemented, for example, integrators, it's not the same as the one in the Modelica standard library, so we have to re-implement that building block specifically to make it work. So implemented the subblocks is kind of the really tricky part because, deadbands, for example, they're not documented at all how it should behave. So you have to design tests to figure that out. So once you have done all that, you set up that template with the new piece you want to test, and you can start verifying the model. So we call this model validation, although it's software-to-software validation. So it's a verification. And we have a flowchart for doing all those steps. So the main steps is actually being able to initialize the model properly and get the same result as the reference tool. So in my field, there is a bunch of tools for steady-state computation that have nothing to do with dynamics. It's called a power flow solution. And what we do basically is that we have some tools that we have built that goes from the output files of that software, and it converts it to Modelica records. So we can populate the exact same starting guess that you would use in the commercial tools. The same starting guess is mapped into our Modelica model using records and all of the beautiful things that you can find in Michael Taylor's book about model architectures and so on, and records. So that's one big piece of the puzzle, and we implement the same model in the commercial proprietary tool, except same structure to be able to create the dynamic simulation. We run the dynamic simulation with the reference software and different Modelica tools. Okay. And once we have done that, we use another tool from the Modelica Association called CSV Compare. We provide the input files of the reference one and the other tools, and we get this nice little picture on the left that has the uncertainty bounds for the error that we want to achieve, and a comparison with the reference. And so, this of course takes a few iterations. So you continue to do this iteratively until you find all of the little quirks of the model and until you have an achievable use. So here is one interesting example. This is called a power system stabilizer. So what it does is there is a cascading controller. So to control the voltage in a generator, you should have an excitation control system that varies the DC voltage of a rectifier or a machine, and you change the field current in the machine to change the AC voltage. So behind that, we add a stabilizer, which is basically looking at a specific frequency range where you have oscillations that are due to the interaction between the machine and the rest of the power grid. So this stabilizer is called PSS2A because it has two inputs. One input is usually the speed, and the other one is the active power produced by the plant, how much megawatts it's producing. So the active power produced by a plant is not a value that returns to the same equilibrium. So the electrical machines and the generators spinning are 60 hertz usually. And if you have a disturbance, they move from 60 hertz and come back to 60 hertz. But the power dispatch will grow or reduce. So you need a run tracking field to fix that, to track where you are and then calculate the error of the signal. So that's the target piece that took a few months to develop what they were doing inside. So when you look at the documentation, we went and implemented what is in the first figure, that is what's in the document. And after a few months, we found out the actual implementation is inverted. Mathematically, the multiplication gives you the same result, more or less, but it makes a difference when you do the implementation that is actually in the correct order. So to be able to analyze what was happening, what was the difference in our implementation, we basically had to look at what the software was producing and then figure out how we had to implement it ourselves to reproduce one-to-one what they were getting. So that's, it was clean room engineering, basically. You're familiar with that. So, right. So then once we have built that, we put it in this test model. The new component is the new component that needs to be validated. So in the library, everything that has been validated against this tool, PSSC, is highlighted with a green, well, this pointer doesn't work. Oh, it's okay. So with a green highlight around the boundaries of the model, so those models have been verified. So you can see general under that, there is the PSSC, the PSS2A model that is being validated. On the left-hand side, you have the reference model in the tool. So then you run a bunch of these standardized tests that we have, and you compare against your three tools, and then you have diagonal impact and PSSC compare their diagonal impact in two of the tools that are supported, or that we know it works. Okay. Here is another example. So this is it's called a DC4B. So this is an excitation system that uses a DC generator to change the field voltage in the AC machine. So these things are extremely old. They're basically used in the oldest power plants. Now, if you look inside of that model, the regulation function, the control function is actually a PID controller. And what you find in the manual is at the bottom. Now, we couldn't get this to work until we started analyzing the integrator. Now, the problem with the integrator is that it's not documented there, but the integrator has non-binding agreements. So when we are analyzing when we were analyzing the response, we'll find out that the behavior was not really the same between the tools. Now, how that was found? We look at the output, that is the plot with the blue, and you can see that it has some saturations with it, so with the min-max limits that are expected. But when you look at the internal state of the integrator, that was really the part that was causing the problem, because it was not documented that it actually has freezing on the state. So to avoid the integrator to keep integrating, basically what they do inside that commercial tool is to freeze the state. But it's not documented anywhere, so we had to implement our own sort of block diagram that has the ability to do the freezing. And since we're in the Modelica conference, you can see how that is done in the text layer, and we have the conditions for the freezing of the state, basically. Okay, so this shows you the end result of that, I think, and might be going up. I'm done. Ah, okay, okay. Well, just you give me a warning when I have 3 minutes, please. Okay. All right. So as I mentioned before, when you run models, with simulation models in these tools, you have the diagram on the right-hand side, and that diagram you can make it even smaller, but you need to have an interconnected system. You cannot just run the model of the controller on its own and analyze what is happening. But what we can do is to run the reference simulation, save all of the internal variables of the specific component, and use that for validation. So the trick that we're doing now for internal components to be more efficient on how we validate is that we gather all the input data in the simulation of the commercial tool, save it as CSV, and the output of that. And then we play it back into the Modelica model to be able to compare with identical input if we get the same output. And in this way, we were able to actually get this implementation to work. So what you see on the right-hand and left-hand side of the model, you see a compute table that has all the inputs. And at the bottom, you see the model, a variant that we made just to compare the cases. But on the right-hand side, you have all the mapping that we made to the actual data. So what this allows us to do, and you see here we have the results with testing with an integrated model is the blue, testing with the commercial tool is the red, or the power system tool, and testing only with the playback of reference signals is the yellow. So this really facilitates the debugging phase basically, because now in Modelica you only have to run this component and you have the references coming in from the tool. So that really saves us a lot of the complexity in the implementation. So here's some examples of interoperability. This work of trying to formalize and use some sort of continuous integration approach to road testing of the new models for the library also helped us to start implementing or making sure that our models work with our tools. And so once we have a student called Giuseppe that was working with Juventus to have the support to have our library work fully in Impact, and then Marcelo has been working with another guy called Glenn to have it fully working in system modeler. So now what you can see here is that we have 4 Modelica tools all give you exactly the same answer. Not only running, but giving you the same answer, which I think it's quite nice. So for an open source tool for us, or an open source library for us, this is valuable because we're not going to force anybody to use a specific tool. They are welcome to use whatever they want. But the other aspect is that if you want to use this open source library for research, for other researchers, they can take advantage of different tools for different purposes, which is, for example, you can use, maybe I shouldn't make examples, but that's one point. No, so here is a similar example, the same for tools, but a larger model that has way more states and so on. So our focus is not performance. I believe that's something for the tool developers to take care of, but that our implementation is accurate. Okay, so this is the conclusions. We try to formalize the steps that we have taken and the process that we have followed. I've shown you how we're now using templates to do all the testing in both the closed source software and using Modelica tools. This sort of is like our knowledge or insight on what works when you're trying to do these implementations. Now, the most important thing is that all of these use cases that I showed you, these are only 3 out of probably, I don't know how many models we implemented with Dominion, and more than 50, I think. So the library now has models that are driven by industrial use, basically. It's not just some IEEE standards. It's actually models that are being used to represent the largest nuclear power plants in Virginia, for example. The ones that they use to do their studies, at least. So it's good. It's really important to have those use cases so that the library can be eventually used by a company, which is the end goal. As a researcher, for me, everything that I do is useless unless it's used by somebody else. That's the point. Okay. We are continuing developing more types of testing on our models, and we hope to have all of this released in the next version 3. And Marcelo, when is the next version 3 coming out? Yeah, when is 3.1 coming out? Thanksgiving? Christmas? That's Christmas present for me. So if you want it, Christmas present. So hopefully by the end of the year we have all of the new models integrated and sure to impact the system on. Thank you. Yes, yes, we will.
How will it be likelihood that will actually convince the person to move forward and do
I guess you can pray always, right? So I think, sooner or later, this industry is being pushed a lot and they're not ready for it. So I think that there are bottlenecks starting to appear because you have only so few of these people that can actually develop specialized models in those tools. So if you want a model of a new device in this PSSE software, it's going to cost you, as I said, up to $500,000. But you have to know how to program in Fortran and in a pseudo dialect of Fortran. So those people are they're in retirement age, the majority of them. So there is an opportunity because of this whole electrification. Hydrogen hype is forcing them to start figuring out how to do it. Batteries are forcing them to figure out this. But it's not just an inertia of the industry, it's the problem that the regulatory bodies are not adopting open access standards. They are in collusion with private companies. So it's a legal, it's a regulatory aspect. I know some of the names, but I don't know about it. For you. I can give you the names, yeah. So the company Dominion that is supporting this is because they have a cloud platform with all of their measurements. They cannot run the models there because the cloud platform is built in Linux. These tools were built in Microsoft and they can't integrate things together, measurements and models. So for them, the solution of having everything using the cloud, they don't care about learning at all. But I can produce a model that gives them the same answer that's in the cloud. So that's the next phase for doing this diagnostics and things like that. Yeah. So there are a family of tools that are used across the world. PSSC, I think, has about 100 countries that use it. It's the biggest footprint. In Germany, they use something else that is German. And it has a big footprint in Europe. It's called Inside Power Factory. They are actually supporting them right now in some ways. So in Europe, it's very different because you have data interoperability requirements from the Commission. So it's written in law that they have to exchange data and they have to deal with a common information model. So some of the work that you are aware of in the World Health Conference of doing the automatic transformation from common information model and PSSC to Modelica, that's something that gets traction in Europe. But in North America, it's very difficult because these tools are already sort of, are colliding with. It's actually, if you look at yeah, well, I think I have to stop actually, or maybe more conflict. We can talk more. But,
thank you, everyone. Yeah, I'd like to present this work that we did with our colleagues at Virginia Commonwealth University, Procter & Gamble, and Tom Sawyer Software. So here's the agenda. I'll give you some motivation for why we did this work, the overview of the kind of modeling that we're doing. I don't want to disappoint anyone. This is not super fancy Modelica from an equation standpoint. Give you a feel for the kind of components that we develop, the systems that we're targeting, what they're doing, and a sample use case. So when we get started in this work, we got started in this project, and part of the goal was to help manufacturing systems move into the MBSE space. And here, MBSE is not what I think of MBSE, because that term means something different to everyone. Here, this means SysML type MBSE, moving away from documents to models, right, but not executable. When they talk about simulations, they want to use the term MDAO, multidisciplinary design analysis and optimization. That's on creating something that's executable and a model that can demonstrate behavior. Typically, there's a gap between these two approaches, right? One gives you a lot of information you can't simulate with. The other one you can simulate. So the goal was to author a dynamic simulation model from a structural model, and I'll show you what that process looks like. So there's a bunch of SysML stuff that I don't really understand, but the goal is to translate that into something that we can simulate in Modelica. So we developed, along with our partners in this project, an infrastructure to automatically generate simulations via Modelica models from the manufacturing architectural model in SysML. So why does this project exist in the first place? This is a DARPA project to build digital infrastructure for improved efficiency in the chemicals and materials industry. So like many things in our world over the past couple of years, COVID taught us some things and taught us some things that we really didn't want to know. One is that it's extremely challenging to manufacture chemicals in the US, and there is potentially a need, like we saw during COVID, to produce critically needed medicines, potentially in a very short period of time. So the goal is to allow manufacturers to explore production duration, synchronization requirements, look at constraints to improve and optimize chemical synthesis processes. Chemicals that are made from many different ingredients, typically in different places, combined together. It's a very challenging process. So the goal is to address challenges in this industry, and partially, and the reason DARPA cares, is to encourage domestic production of medications and a broad range of APIs, active pharmaceutical ingredients for drugs in the US, instead of, different API, instead of overseas. So one of the things that became problematic was we might want to make a lot of COVID vaccines, but we don't have the pharmaceutical ingredients in the US to do it. Can you manufacture it? Can you support your citizens? Can you support your military? And what if some of those ingredients are coming from other countries and maybe they want to use those same ingredients for their own population? So drugs, and including some of the in-demand APIs related to COVID-19 and others on the strategic national stockpile list were kind of important for driving this project. So this is an overview of the entire process from a modeling standpoint. So the first thing that happened, and this was done by actually VCU in conjunction with Procter & Gamble, is they created SysML models in IBM Rational Rhapsody for a given manufacturing process. So to manufacture a given chemical, they created SysML models. They also did a bunch of research and surveys on equipment databases in the US. Who has different kinds of equipment? What is it certified to do? How large is the equipment? How much can you manufacture? So based on the SysML model and this equipment database that was generated, there's a process to create a fully parameterized Modelica model using software from a company called Tom Sawyer that creates a Modelica model that we can then simulate. So from the SysML model, we get a Modelica model that's executable. That Modelica model we then use with Model on Impact and its simulator API to run the simulations, and then we pass key simulation results, things like process throughput, process time, back to Tom Sawyer to visualize the results and also as part of an optimization process. Could we manufacture in a different way? What if we allocated equipment differently, right? Maybe you want to make this ingredient here instead of there. Does that lead to a shorter time? So this is kind of the full process. This is a lot of stuff. It was a work of a lot of people. And today we're just going to focus on this piece in the middle, which was where Modelon was primarily involved, which is in the development of this Modelica library and then the resulting models. I'll show you some models that were created and what they look like. So this approach is focused on simulating the manufacturing process layout, and our goal is to analyze how long does it take to make this chemical and how much yield do we get, right? So these are the two things that we want to get out of this model. So some of the challenges that are here as part of this work. So the process steps for manufacturing different pharmaceutical ingredients are not wholly documented in public references. So certainly the companies that make the different ingredients, they of course know exactly how to do it, but for for example, the grad students at VCU, they're out there looking at public references trying to figure out how is this thing made. And they'll find stuff partially documented, very high level. So we don't have like perfect, great data to start from. And the models here are expected to be used in massive optimization processes. So they're intentionally implemented to be very low fidelity, computationally fast, and we use time events. There's actually no ODEs in these models. I'm sorry to disappoint you. We're basically doing something that you could kind of do in Excel, but obviously nobody wants to do that, right? We can do things object-oriented and trigger things, and that's important, but I mean, from a computational standpoint, the equations that you're seeing here are not fancy. So this is an example of a model that we'll talk about in a little bit it's one part of a process. So what do the steps look like? So basically we're implementing all of the steps as individual primitive components. So each stage is responsible for doing a couple of things. It computes its status, how long does it take to complete that stage, and what leaves it, right? Given what comes in, how long does it take, and what's leaving. So the material characteristics, what leaves, and the status are going to feed successive stages, right? I heated it, now I can go and mix it with something else. Or I need to hold it in a tank for 30 minutes. When that's done, it goes to another, gets pumped to another tank, right? These are the kind of things that we're gonna simulate. These stages are ordered, so we can use causal interfaces, right? I mean, the process goes from A to B. So here you can see the connectors that we use. We have a process input connector and a process output connector. On the connector, it says, what is this species? How much mass, and what's its temperature, right? And we're using input and output connectors here. So in a given process, right, these things can change. The mass can change, the temperature can change, and the species can change because we can have reactions. We also have a logical interface because we need to trigger the downstream processes. So the stages share their status with adjacent steps via the Boolean complete variable that you see there. And a stage can depend on multiple previous steps, right? Sometimes this thing needs to happen and that thing needs to happen before you can start. So the trigger that you see on the input is actually a Boolean array. And we don't begin processing until all of the triggers are true. And then we start an internal timer, and then we figure out how long this step needs to take. We also have a conditional option. So if you don't want to trigger from outside connections, you can also just trigger conditionally based on time, like start at a given time, and then you don't have to connect up with anything. But most of the work is done by connecting something to the input trigger. So to handle material data and material processes, we use a very simplified approach because we don't have rigorous species information and property information here. It's very high level. So we have basically a species array that we create and thermophysical properties, right? And that's what's going to be used with inner and outer to determine the properties. And here you can see, for example, what we're doing in the list. You can see a list of species. So we start off with some individual species, and then at different points in the process, species will be combined together, and we just treat them as if they're a new species, right? And the reason for that is because nobody knows what the properties are of DCM plus tropine, or, you know, I mean, so like we're really drawing with crayons here. I mean, this is not, you know, we're trying to figure out, is this process going to take 5 hours or 3 days, right? I mean, this is not something where you're going to like, oh, it's 20 minutes or 21.2 minutes, right? This is really, really high level. So this is where we treat the material data, and this is how we calculate the properties. Here you can see a list of properties, things like densities, thermal conductivities, specific heats, diffusion coefficients, latent heat, depending on what we're doing as part of the process. And I'll go through all the component models in a bit. The very simplest component model that we have is just time. And if you look at the recipes, hold in a tank for 30 minutes, right? Mix for 45 minutes, you know, stir for 30 minutes. Those are part of the processes for making these. So we have a timer, right? And it's the simplest component, right? You just tell it how long is the time. So this is fed from the SysML model, right? The SysML model knows what this process is and can feed these parameters. So this is a pure delay, no material modifications. What comes in is what goes out after a period of time. No mass is stored, no heat is transferred, and when the stage is complete, the output connector gets the mass and temperature of the input connector. So that's what then gets passed on to the next component. Simplest component that we have, so we create a couple different icons that all are basically these time components, so that when you see the process laid out, you can say, oh, that's a hold or a stir, because sometimes people want to know that, but underneath they're all just a time. Just a different icon. We also have rate components. So these are stages that operate at a prescribed rate. So unlike the time components, the processing time is computed based on a rate equation using the ratio of the quantity to be processed and the processing rate, right? So these will scale with the amount of mass and the density of the material on the input connector. And we have typically fixed rates that we specify via parameters, because that's all we know. So that's a rate component. We also have a mixed component. So this guy has a component array of inputs. So if you need to mix multiple things together, we connect them. And this will simulate stages where materials are combined over a fixed amount of time. There's many parts of the process that say, take this stream and that stream, mix them together for 30 minutes. So the outgoing species is a new species in our list because of the way we've handled the material model. So you have to tell it what's coming out, right? If DCM and tropine came in, then the species index of DCM plus tropine would be what's coming out. We do conserve mass, so the outgoing mass is the sum of the incoming masses. And the temperature of the outlet material is just the mass average of the incoming material. This is completely wrong. This is not conservation of energy, but we don't have really enough information to do it properly. But we do have information about what the temperatures probably are at various parts of the process. So that's kind of the best we can do. But yeah, I recognize that's not how you do conservation of energy. Also have a reaction component. This again uses the array inputs. You can combine multiple materials together. They're going to create a new outgoing species. You give it a parameter. What's the outgoing species? How long does a reaction take? What's the yield? So not every reaction is going to give you a full yield. Sometimes you're only taking some material out from the reaction. And what was the temperature change, right? So this is not physics. This is like information you're telling me, and I can just report it on the output. So nothing fancy, but this is how the reactions are handled. The original goal when we started this was actually to make really high quality physical models that we were going to write all the right equations and do proper conservation laws, and they couldn't find nearly enough information to support those kind of implementations. There are many times in these processes where we need to pump things. We need to move liquid from tank A to tank B or whatever. So we have a couple of different models that do that based on what you know. We have a volumetric rate component. You just give it a volumetric rate that you might know from your equipment database. And then based on the density of the incoming material and its mass, you can then say that's a certain amount of volume, and then you'll know how long it takes to process that. You see some equations there. There are some components that have a little bit of physics inside of them. We have a liquid transfer component. It's similar to volumetric rate, but we try to calculate the rate given a pump power and some piping information, then figure out how long it would take to move it. Important process in these manufacturing is the dissolution process. So how long does it take to dissolve a specified mass of solute in a vat of material? The solute can be specified as a parameter, so if you don't actually want to track the solute, you just want to have it appear at this point and be dissolved, you can do that as a parameter, or you can have a conditional connector where you can actually include the transport of the solute as part of the process. And the time is just calculated from some mass transfer calculations for a stirred vessel. Doing mass transfer, we'll probably have to do heat transfer. There are many times where you have to take the material, heat it, keep it at the temperature for some period of time. So we have a very, very simple heat transfer model, assuming a liquid in a fixed volume stirred vessel. So given the temperature that it comes in, the temperature that you want, the temperature of some heat transfer fluid, you can basically do some really simple calculations for how long that would take to happen. Part of the other processes we need to consider are drying. So there are times where you mix with stuff, you wash, then you need to dry. So we have a drying model that accounts for the addition of heat to evaporate some fraction of the incoming stream and then provide you something else going out. The species depends on whether you care about what you dried or what's left, right? So you can tell it in the model What should go out is what was evaporated or what was left. So you can decide that. So this handles both drying and distillation. It assumes super simple models, fixed rate heat transfer that you give it, that we can then use to figure out how long it takes to heat the material to the vaporization temperature, and also to add the latent heat so that you actually can evaporate. There are processes that include filtering and washing, so you need to take liquid, pass it through a permeable solid. So we have some equations to try to calculate how long that would take for a given amount of liquid, given a certain characteristic of the solid, its permeability, its area, the viscosity, the length, and the pressure that you operate in. And then we can basically take some fraction of that, because we can handle a yield fraction, and that will then pass on to the next component. In addition to the filter, we have a wash component. The wash component is very similar to the filter, but it also allows you to put the liquid in too, so you can track the liquid separately and then specify what the output is. So the wash is a little bit different, because you can't start the filtering process until you've delivered all of the liquid that needs to be used to wash. Phase cut is just a separation of an incoming species into two different ones. So this is a process separation step. There are times where it says, okay, take this and take out, cut the phase so that you only get this part out. So we take the information on the input connector and we'll separate it based on some fraction into two separate outputs that are different species. And you can also specify a yield fraction so that you can get some fraction out. None of these processes are 100% yield. Then we also need source components. So this provides a fixed amount of mass at a fixed temperature and a specified species. There's no complete signal on this because it's a source, right? So it starts our processes. And if you need to account for the delivery of whatever is on the source, you do that with the downstream component. And then we have an end component that just records the overall completion time and a discrete variable. It'll also terminate the simulation, because we don't know how long these simulations are going to last, right? We don't know how long it's going to take. So we typically set really, really long end times, and then this block can terminate the simulation when the processing is complete. And then the final production species, mass, and temperature are on the input connector. One of the things that became apparent as we were working with the Tom Sawyer team that was producing the Modelica models was that there are many processes that happen, there are many patterns that happen in parallel. So there's combinations of processes that are often performed together. And so because the Tom Sawyer team had to generate the Modelica code and all the connections between components, if there were some things that they were doing over and over again, we thought, well, why don't we just make you an assembled component so that when you see that pattern, you don't have to instantiate 7 or 8 components and all the connections, you just take this aggregate component. So they were super excited when we were like, yeah, this is trivial for us, when we told them that we could do this, because it really saved them work on how to create the Modelica code. So one of those is heat transfer and dissolution. Those often happen together. The dissolution process often tells you need to heat the material, and we treat dissolution isothermally, so if you need to heat, we need a heat transfer component next to it. So we created those as an aggregate component, and that's one of the ones that you see there. And add liquid and wash is also a standard pattern. So when you need to wash it, you need to add the liquid, so we combine the wash with the volumetric flow rate into one of those aggregate components. Again, it's not doing anything other than instantiating multiple components underneath, but from the standpoint of the team that's generating the Modelica code, it simplifies their life quite a bit. Here's an example. This is for the synthesis of a chemical called tropine methane sulfate, which is a precursor in the synthesis of atropine, which is our actual use case. So if you don't know, and I didn't know, atropine is a prescription medicine that's used to treat low heart rate, and it can also be used as an antidote for certain kinds of poisoning. So there you can see the kind of information that was collected on the creation of tropine methane sulfate. So when they went and figured, research what it takes, they would see things like add dichloromethane, DCM. So you can see we have a DCM source. Add solid tropine, that's the source underneath them. Mix them together, then heat them, then dissolve the tropine in the solution, then add something else, methane sulfonic acid. Mix them together, then there's a reaction, and then that creates tropine methane sulfate, and you need to transfer that from the reaction vessel to be used in some other part of the process. So this is one small piece. This was one of the first things that we made because it's got enough things to be interesting, and it's one small piece of the entire manufacturing process. So what do we do when we build this model? What does it look like? So when we simulate it, you can do things like shown in the graph, which is basically look at the complete signal for all of the intermediate stages, right? So, you know, this illusion was complete at some time, right? So you can see how the progression works. And then you can see from the sticky and impact at the end of the sim, it took us, in this case, 1,147.84 seconds to do this process. The mass was 11.34 kilograms. The temperature was whatever it is, and whatever comes out is species index 7. So this is the kind of information that we then feed back to Tom Sawyer, and then they can say, well, what if we allocate the equipment differently? What if we make this process differently? Those are all things on the table for part of the optimization process. So our goal is to provide the libraries to simulate this, the simulation infrastructure to run the models and get the results back. This is a more complicated process. So actually the model that we showed here, so the output of it is actually this very top input here. This is more like the full atropine synthesis process. So here you can see there's a lot more stuff. You know, this is the recipe that they were able to find, right? You add stuff, you wash it, you dry it, you heat it. I mean, whatever is part of the process. And so these are things. Now we're talking about, you know, much longer simulations, right? I mean, these not CPU time. I mean, these things are algebraic; they run instantly. So, but now you can see it's taking whatever that is in seconds, which is a really large number to do. And you can also evaluate, you know, when you go back through, you can say, well, what's taking so long, right? Why does this take so long? Where are the processes? Where are the bottlenecks? You know, what if we did this part in parallel? Could we change it around, right? That's really the goal. I mean, these simulations are simple and trivial. So, you know, there's no glory in being able to do this. You could do this in Excel spreadsheet if you wanted to, right? But then the question is, what are you going to do with this, and what kind of things are you going to learn, and how are you going to make the process better? So in conclusion, what we did here and what we described was a library that we used as part of this DARPA project that we developed for supporting digital infrastructure for chemical and materials industry. We integrated this library into this full software stack that also was automatically creating these process models from SysML and simulated with Model on Impact. I hope I didn't disappoint you. Maybe some people really wanted to learn about how the models came from SysML to Modelica. I really wanted to learn that too, and I was hoping we could do that as part of this paper. So while we demonstrated this initial use case, this is not the end, right? The future work is really going to be focusing on analyzing the supply chain, identifying gaps in key drug manufacturing, and optimizing the process. There are other publications involved, including some from our partners that are focusing on that aspect of the SysML to Modelica side. I wanted them to be part of this publication. The guys at VCU did not want them to be part of this publication, and there are also some other companies that are being formed around this process. So there's kind of a lot of stuff going on that allowed only this part to be the focus of what we showed today. But there's a lot more stuff and a lot more interesting things, and I hope in the future we can talk about some of these other parts too. So anyway, thank you. Yeah.
I mean, I think the visual, the philosophy
Yeah.
and then the cool thing I would like imagine doing was the methodologies and how it's like change and see how the
Yeah. 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 seeing the complete signal go from true to false is not super exciting.
And also the presentation of the data.
Yeah, it's just when that state, at what time is that state? But you need to do a lot more to figure out what the concerns are. That may have only finished there, but if you have to sit it in the back before the point, and you can't get rid of that state.
So I mean, I only work for quite fun. At least that's the having allocation. Generally, basically, when you start to get it, you like in everything, you are quite.
Yeah.
So how long does it take? Well, I'm especially in winter and in summer, it will be different time. That's what. So you
And it's hard to separate those, right? So I mean, I think the uncertainty is a good idea, but if really everything is so uncertain, I'm not sure that once you get out of it, I don't know what you might learn, right? Other than you don't have an option.
I mean, I think that somebody that we have, I mean, the fact, many different and right off.
And it would be absolutely easy to just take all the parameters that you're feeding and get them all to the distribution and say, well, okay, the overall process time has a distribution that looks like this, and this is one standard distribution. That's definitely doable. And that's actually part of, that can come to you from the automated generation process, where now these parameters have been given you the distribution, or it could be you get one model and then you could apply that on top.
In the system level part, like if you want to have all the required specifications, do you check the requirements on the Modelica side or the impact side, I guess?
Yeah.
Or is that checked on the Tom Sawyer side?
Yeah, I think that's on the Tom Sawyer side. I mean, so what we checked was that, so it was kind of a crazy process. As an outsider, like the whole system out thing was like, if our goal was to get to this, what we had to do with the system outside to get this model was ridiculously complicated. It was like connection, like we got this meeting, I can't even see the diagram, like you gotta zoom in, it's 800 pages long, and you can't see. So what we did was, we started with this recipe, they implemented it. We said, okay, I can implement that manually, right? This is the way the model should look. And you now, when you automate the creation of that model, you gotta create the same thing. And so that's how we So we made stuff manually, we did the mapping from what they had in the system else, what the development components were, and then figured out that's the process. You create manual models or automated models. But yeah, the requirement side, that was, and they were using all kinds of ways. I couldn't tell if they were using SysML in a standard way, or if they were like taking parts of SysML and using it in a non-standard way to help support this. I couldn't really talk to them ever at all.
I'm curious because there is also this, on that area, they have executable UML account that you can generate something that you end up with an simulation of the UML model. And I always thought that, okay, and then now that completely flexible, just sort of doing stuff.
Yeah, I mean, it seemed much easier to me to get to this, right? And there were many times where we forced things back on the system outside because we needed, if you want to simulate, like, I need to know what species that is. I need to know, what temperature that is, or what is the process supposed to be here. And those, in many cases, those are not things they plan on putting in the system outside. And so, well, if you don't put it there, I can't simulate it, right? You gotta get, this is information that we need to be able to make it executable. So there's a lot of back and forth, right? The system outside started much simpler than it ended up because we need all this information. And then we didn't even talk about, well, what if you want a more complicated model than these? What kind of information would you need to provide, right, to be able to support that kind of executable model? That's why we ended up with these small models. Because otherwise it would be so much information and they would struggle to do it.
seems like in a lot of processes that I'm familiar with, there's very limited information. Like, for example, fertilizer. Fertilizer packaging is good. My father was plants for that. You got both fertilizer, chunk it in trucks, and you go out and mix it, and so on. Or beers in the back, etc. like that. Yeah. It's the same thing, pretty much. But they also don't know how to consider, when do we have to have the trucks there? Yeah. Or what if there's a hurricane coming? Yeah. How do we replan the whole product? Yeah. So it's very, very, it answers all the questions that are more from the production.
Yeah. And I think that's really, I mean, that's why this project is in the first place, right? Like, look, you might need to make critical medicines. Can you do it at the scale that you need and the time that you need? Right? And I think COVID is sure that was a challenge. There are some things you probably don't have enough capacity to make, and if you're relying on people outside of where you can control, you may not get what you want in the time that you want. That's here.
Yeah, I think the bottom line is, the US still have actually large molecule stuff. So COVID vaccines, which is molecule away from 100,000 millions of protein, that costs enough money. There's still enough margin and money. But small molecules, they're produced in India, Vietnam, and China. China is getting expensive. And so small molecules, most of the antivirals, so the actually medicine and not the vaccine. That is all small molecules. That's all produced. That's a new way from Vietnam, and go that from China, because that is.
And there's a lot of, I mean, while we got a fully parameterized model of simulating, there's actually a ton of work up front from the Tom Sawyer side, because they have to throw out based on, regulations, certificates, what you're allowed to make. So there is all this equipment, but there was this whole process at the beginning before we got something that was actually viable to simulate, where they have to look at all the equipment and what they're trying to make and say, oh, this plant can't do it because they don't have, their vats aren't big enough, or they don't have the permit to make this sort of thing, right? So there was all kinds of upfront stuff to even get to the point where there was allocation of parameters for us to simulate, and that was all. I mean, it's really cool stuff.
But I mean, it seems like you could also apply this to so many other things, making that field. I mean, if you don't, we haven't probably developed the cost of money that we. But it's interesting that you can do these things anyway with Modelica, but you get the information.
Yeah, I mean, it's super trivial, like, kind of right now. I mean, it was almost silly, we were just writing about it, right? But I mean, if you think about it, it's nice to be able to graphically lay stuff out, connect, see how things are connected together. If you were doing this in a scripted way, you really hard to interpret it.
You're most attention on because it's located in that direction. From me, from my point of view, if you're going to make decisions on buy tremendous amount of certain precursors for medicine and for billions of dollars, I think it's a different way of thinking about it. Just because it doesn't have differential equation.
And I think
it's a different, it's completely very interesting.
You need really something more. You want to look to, if you look at the communications, I mean, you can definitely easily millions of potential production supply chains. With verification and long delay, there can be one part of medicine you need to make that part, can be one in that part, and you need to combine them. So there's actually logistics parts combining these things.
Yeah, so for example, I mean, if you, speeding up one process may not give you improvement overall, right? If you gotta wait for the other one to finish, right? It's like, it doesn't make sense.
You could book in their energy costs, even if you wanted to, right? So in the process, you can do it, it doesn't matter how long it takes, you do it at night with an existing and then it costs you a fraction.
Yeah. And yeah, I mean, cost is definitely something, I mean, we weren't doing any cost part here, it was only about throughput and time, and also So if anyone wants to see these models, we can run them. They run super fast. We have them on the impact side. You can take a look.
So what is this library called in GitHub?
I think the name, the project is called Ask ESP. So I think the original, so that's what we named the library. But the original goal is that policymakers could go to tools like this and ask these kinds of questions. And I think it's a long way away from that, but that was the goal of this project. The library is called Ask ESP. Thanks.